All right, good morning. Well, we are really lucky right now. It feels pretty comfortable in here. The rooms I've been in earlier today, man, they've just been an ice box. So I'm sure it'll get there at some point. You need to start bringing a jacket and maybe like a margarita to class so you can either keep warm or cool off.
Dr. Beanick had put a requisition in at Small Rock.
Uh-huh.
Like 60 degrees.
Well, yeah.
Yeah,
I think
they approved it.
the real way to control the heat, I think, is going to bring an ice pack and tape it to the wall if it's too warm so that we can trick it to thinking that it's colder. And then if it gets too hot in here, we'll get a hair dryer and blow it down with the hair dryer, and then it'll switch itself off. So that'll be our new way of controlling the temperature in this room. The next homework assignment you've got is due on Tuesday. And today we're going to work through an in-class exercise. I also forgot to hand out the quiz papers during the last class, and so I gave some of those out during the lab. If you haven't yet picked up your quiz, you can get that at the end of class. It'll just be here on the table. We're going to continue talking about hydrostatic forces on flat surfaces. This is a key point of the course, and we want to prepare you for a lot of things in this program, one of them being the FE exam. And it's pretty common for there to be hydrostatic force on flat surface type problems in the FE. So we want you to be really proficient with those. We did some examples in class, and hopefully you've been working on homework problems related to it. Let me just walk you through some of the key ideas on the upcoming assignment. One of those problems is 72, so let's look at this. So we have a gate that the water is acting on, and they have put a pivot point in the centroid of the gate. But what we know is that the force is applied below the centroid. And the deeper we are down underneath the surface, the closer together the point of force application and the centroid are. But the force is located at YCP, which is always below the centroid. So what is going to happen is the force is going to be acting on this gate, and it's going to be causing the gate to rotate in a counterclockwise way. So to prevent that, a block is in place. So first of all, to find the magnitude of the force, we use this formula. The force is the pressure at the centroid times the area. And we can determine the pressure of the centroid with delta H times gamma. And delta H is given directly on this sketch. We're just couldn't be more lucky. That dimension is provided directly. So we have to think in 3 dimensions to calculate the area moment of inertia. This is a 4x4 gate, so we can see that height dimension with this 2 meters and 2 meters. It's also 4 meters into the page to make it a square gate. So this is a relatively straightforward problem, but it's the moment analysis at the end that sometimes can be a little bit tricky. So what we can do is we can find the gap distance between the centroid and where the force is located. And at the bottom right is the formula for YCP that you've seen a couple of times so far. But remember, I also told you another thing we occasionally do is we say YCP minus Y bar is I divided by Y bar A. So here it says I bar. I bar and I are the same thing, but it's just the area moment of inertia. So this gap distance, YCP minus Y bar, that's this. It's from the red dot to the force hydrostatic. Because since it's vertically oriented, remember Y bar and delta H are the same when it's vertically oriented. So here is that 10 meters is the Y bar. But what we really want to know is what's the moment situation happening, because we know that the force of the block is acting at a distance of 2 meters with some unknown force. You'll calculate the hydrostatic force, and then you'll need to know that gap distance to know the moment distance that's effective for the counterclockwise direction. So the reason I brought this up is just to show that sometimes it's convenient to rearrange the formula for YCP. Okay, another one of these problems with hydrostatic forces on flat surfaces is the force needed to open the gate. So what's keeping the gate closed right now is the pressure of the water that's acting against it. So we have these dimensions here that the vertical component of the gate's height is 4 meters. And we can see 3 meters is the dimension from the hinge to the bottom edge of the gate. So that tells us that the physical height of the gate is based on that 3, 4, 5 triangle. Now you need to also determine where is the hydrostatic force acting on the gate. Now this one's not vertically oriented. So when you go through the process of identifying the centroid, delta H is usually pretty easy to calculate, but Y bar and YCP can be a little bit trickier, especially here because this 1 meter dimension that they've given you, that's the vertical component of the distance from the hinge to the water elevation. YCP isn't that vertical distance, it is the inclined distance. So you're going to have to take the 3, 4, 5 triangle and find out what is this blue, I'm sorry, I know my colors, green. This green segment of the line from the hinge up to the water surface, you're going to have to find out, okay, the vertical component of that is 1, so what is the inclined section? So what's the hypotenuse length of that triangle? I won't give it all away, but it's related to the 3, 4, 5 triangle because it's an extension of that same angle all the way up to the surface. And then, once you find where the force is located, and actually the moment distance isn't going to be the same thing as YCP. YCP is from the water line to the force, but the moment distance is just going to be from the hinge to the force. So you'll have to subtract out that segment length from YCP to know the actual moment distance that's acting in the counterclockwise direction. And then the force up, this P, is what we're trying to find. How much do you have to pull up? Like if you were in a boat and you were lowering a line down, how hard would you have to pull to open up that gate from the boat? P. The moment distance isn't the entire gate length, is it? Because of the direction. If the force was this way, it would be the entire gate length. If it was perpendicular to that gate direction, but since we're pulling straight up, now the effective moment distance is just the 3 meter dimension that they've shown. So I think the trick to this problem is maybe the geometry. And I want to just emphasize that it's unfortunate they called that P in the problem because we usually use the letter P to mean pressure. They don't mean pressure. They're just talking about some force that's applied to open up the gate. It's coincidental that it's the letter P. So any questions about this homework problem? It all boils down really to the length of that segment. That's maybe the stumbling point if there is one. All right, so to reinforce these ideas, I think it's one thing to hear it, but it's another to do it. And so I'm going to stop talking because I think that's when students learn the most, is when I'm not speaking. I'm going to give you an in-class exercise. It's got a front side and a back side, some problems where step by step I'm going to take you through what you need to do to find these hydrostatic forces and so on. So you're welcome to work on this with a classmate. In fact, I prefer it. I like it being noisy in the classroom when there's an in-class exercise because I think noise means learn. Oh, that's the wrong one. You don't want
No.
engineering economy. Yeah. There we go. more. That ought to do it. There we go. All right, so circular plate. Let me go back to the geometric parameters for a circular plate. That was earlier in the notes. Let's just go get the area moment of inertia, and we'll pretend like we don't need to know the area formula. Let's see, where is that? There we go. All right, so this one's circular, so let's get the I value for a circular shape is pi r to the 4th divided by 4. All right. Yeah, I'm sure in my case it wasn't the teachers that was the problem. It was me. Yeah. Okay, up on the screen right now, I've got how you find the delta H. So it's all of the geometry backflips that you have to do to find the inclined distance to the edge, and then adding on the additional inclined distance from the edge to the centroid, which is just half of the diameter. And then finally, how to take it back up, straight up to the surface to find delta H. Sure. You can definitely use the angles. You don't have to use the similar triangles. Really? Might be cosine when you're supposed to do sine. Yeah. I always have to kind of refresh my memory on that. Let me scroll down to the rest of the solution now that you've seen how to calculate delta H.
After I've been in engineering classes and go back to that's what just so I can memorize I like to learn concepts. It doesn't even go. That's how like part of our difference following
length. So to the centroid from the hinge, 3 meters, right? So it's only inclined 30 degrees, so most of that distance is the vertical, right? So sine of 30 is 0.5, cosine of 30 is 0.866. So we can just by inspection see most of that distance is going to be vertical, so we should use the cosine rather than sine, because the result of the cosine 30 is going to mean 86.6% of that length is in the vertical direction. So if you can never quite remember the fundamentals, like your rhymes of sine versus cosine, just multiply it out and see which is the most reasonable of them. Once you find the delta H, then you're also going to need to calculate the pressure at the centroid, and then the magnitude of the force is dependent on the physical dimensions of the gate. Here they told you it's 2 meters wide. Any questions on this first part, on the first 3 bullet points? I didn't write it on the board, but many of you remembered already that the area moment of inertia for a rectangle is the width parameter times the height parameter cubed divided by 12.
Now that's also going to be, let's say if the longer end was turned down.
Yeah.
That's still going to be, your B is always your longer end, correct?
No, I'm glad you asked. So B is the vertical one.
Always.
Yep. And the way that I remember that is, it's the vertical components that matter the most to us in the hydrostatic equation, because we're going up and down through the fluid. That's how the pressure accumulates. So you cube the vertical dimension rather than the horizontal dimension. Yeah, it's not necessarily which one's longer. It's just coincidental in this case that it's longer than it is wide. So here, anybody want to explain why I suggested finding the distance between the centroid and the center of the pressure rather than just leaving it as the y bar? Why is finding that distance more useful? Right, for the moment distance, you're going to use it. It's not the only component of the moment distance, but if you add it in here in this little sketch here, I kind of show what that gap distance is. So it's the distance between where is the centroid and where the force is applied. And again, the force is perpendicular to the orientation of the plate, and so it's got an upward direction. And this is a net force. It's not like there's just one hydrostatic force out there. What's really happening is there's a distribution of pressures acting over an area. So we could break it up into little segments. We could make like a mesh, 1 centimeter mesh, and each mesh point has its own pressure and its own little area, and we integrate it. And we would get the same thing as if we go through this process and find the single resultant hydrostatic force. So all we've been doing is finding the resultant hydrostatic force and its resultant location, which is the equivalent to the real deal, which is, there's a little bit of pressure at the top of the plate, the pressure is gradually increasing, and it's acting over that plate in a linear way. So our moment distance would be the 3 meters plus the gap distance for the counterclockwise rotation, and then from the edge down to the force of the block, 6 meters. They're going to have to start renaming it clockwise and counterclockwise because nobody uses really analog clocks anymore. I wonder what very few people wear. Anybody wearing it? Oh, there's one. All right. Oh, it's dead? Just looks good though. Yeah, it's right twice a day. Any questions about this one? All right, I'll leave it up on screen for another moment or two so you can finish copying things down if you need to. Let me just interject with a note about precision. So don't round off too early. For example, if you rounded off this delta H to be just 5.6, then you're not able to report the pressure to anything other than the nearest thousandth of a Newton per meter squared. So although I write down 5.598, it's actually 5.598 ... and I keep all those extra digits in the calculator so that when I multiply it by the unit weight, I can report the pressure to the nearest Pascal. So I have 1, 2, 3, 4, 5 digits of precision because that and more is in the calculator. So the warning is don't round off too soon. And if you write, it's okay. I don't want you to have to write 16 digits on the paper, but it's just kind of taken as a given that you're going to keep all of that precision in your calculator as you work through the solution. All right, we do have one more example we're going to work through before we finish for today. I'll just pause for just another moment to make sure everybody's got this. Yeah.
I was just wondering for your YCP,
Yeah.
why bar was added? Or do you need to add Y bar to that?
Good question. Good question. If we wanted to know YCP, then I would have to add Y bar. Yeah, so let's go up to the drawing here. So I'm going to just gesture at the screen here. So let's say here's the hydrostatic force. It's below the centroid. So Y bar is the distance all the way up to the water line. So if I wanted to know Y bar, then yeah, I'd have to, in the formula you're asking about, move that to the right side of the equation. What I'm saying is it's actually not so important how far it is up to the surface, because ultimately what we're going to be doing is calculating like a moment analysis about this hinge. And so it's how far away it is from the hinge that I really care about, not how far it is from the surface. And so by having YCP minus Y bar, then the result of that is how far apart this and where the force is located is. So that's why I kind of rearranged the formula that you're asking about here, right? Yep, exactly. So, YCP would have Y bar on the right side of that, but what I really want to know is, see where it says here 0.4641, that's the distance between the centroid and the point of application for the resultant hydrostatic force. Does that answer your question? All right. I'm glad you asked it because it's an important point. Are there other questions? Okay. Great. So you can hold on to this, and hopefully it'll be a useful resource for you as you work on the homework that you've got on your plate. Let's also now look at another example that makes a different point. Okay, what if, the extreme of an angled plate, we started with vertically oriented plates, and then we looked at some that were at an angle. What if we make it horizontal? So it's all the way horizontally oriented. That's what this is. What's the hydrostatic force that is acting on it from above? We can use the same techniques that we've used so far to answer this. The equivalent hydrostatic force is going to be, the force is the pressure at the centroid times the area. Where's the centroid of this? Well, pressure at the centroid, delta H times gamma times area. That will tell us the force that's acting from above. Okay, the delta H distance is 5 meters. It's just that given dimension from the water surface down to where the plate is. So it's 5 meters, and then the water in this example is the fluid. So the unit weight, 9810 newtons per meter cubed. And then finally the area, the physical area that the pressure is acting on. So think in terms of pressure. You know, there's a certain pressure at this depth, and the pressure is pushing down on the plate. It's perpendicular to the orientation of the plate, so there's this distributed pressure acting over the entire face of the plate, and we want to represent that pressure over an area as though it's a single force. So the area is 2 by 3, so that's 6 square meters is the plate area. So the magnitude of that force is 294,300 newtons. Okay, the second way of looking at this is what's the weight of the water above the plate? So weight of the water. How can we calculate that? How can we determine? Good. Volume times specific weight. Okay, so we have to think, all right, if this is I'm not good at drawing, and I'm really bad at drawing in 3 dimensions, so let's see here. Yep. Okay, it's 3 meters by 2 meters. What we're asking about is how much water is above that plate. So we have to consider the depth parameter, so it's 5 meters of depth. So it's essentially like a box of water above that plate. So the volume is going to be the volume of the water above the plate, 2 meters by 3 meters by 5 meters. And we'll multiply it by the unit weight, 9810 newtons per meter cubed. Just for those who are following along at home, there we go. Here's the first part. If you do the calculation, you'll get the same thing. 294,300 newtons. This is going to be really important to us when we start working on curved surfaces. And what this example is meant to demonstrate is that the vertical force is equal to the weight of the water. So the hydrostatic force can be broken up into a vertical and a horizontal component. In this case, there was only a vertical component because the plate itself was horizontal. The vertical component of the hydrostatic force is equal to the weight of the water above the shape in question. So it seems really straightforward. But when we start talking about curved gates, it's less obvious. That's why we start with this example. It makes the point that the vertical component of the hydrostatic force is equal to the weight of the water. I should type that in as a conclusion here. This is what you're supposed to draw from this example. So the weight of the water is equal to the vertical component of the hydrostatic force. And to be continued on that. The application of it is to be continued. That's all I've got for you today. Let's just flip back to those announcements and see that you've got a homework assignment due on Tuesday. I won't see you between now and when that's due unless you come to my office, which I'm glad to help you. Stop by and I'll do my best to answer your questions. If you want to send me an email on the weekend, I'll respond as quickly as I can. And if you tell me about which problem you're working on, if you just say on problem 1, what should I use for the unit weight? I may be out in the woods and I don't remember what problem 1 is, and so I'll have to wait until I can get a textbook, but if you like send me a picture of the problem you're working on and a picture of the problem statement and say, here's what I'm doing, here's what I've tried so far, like, give me a little bit of resources, then that may enable me to respond more quickly than I otherwise would be able to. All right, have a good one. I'll see you next Tuesday.